In this video, I will be discussing about continuous probability distribution. Now, if the random variable x is a continuous random variable, then the probability that this random variable takes on any one particular value is generally zero. In order to arrive at a probability distribution for a continuous random variable, we note that the probability that x lies between two different values is meaningful here. For example, if a person is selected at random from a large group of adults, then the probability that his height x is precisely 69 inches would be zero here because we are talking continuous random variable. In other words, the probability of the specific value for a continuous random variable is zero. However, there is a probability greater than zero that the height of this person is between 68.5 inches and 69.5 inches. In simple words, we can obtain a probability for the continuous random variable when our random variable is given in an interval. But there is no probability for just one specific value of the continuous random variable. So even though the probability distribution of a continuous random variable cannot be presented in tabular form because in a continuous random variable there are uncountably infinite elements in our sample space. But this can be stated as a formula. And such a formula would necessarily be a function of numerical values for the continuous random variable x, and as such will be presented by the functional notation small f of x, wherein we call here our PDF. PDF means probability density function, because in the discrete case we call it PMF, probability mass function, but here we call it probability density function. Now, let's proceed to our definition 6 here. A continuous sample space is a sample space which contains an infinite number of possibilities equal to the number of points on a line segment, which means that there are uncountably infinite elements in our sample space. So, therefore, our continuous random variable is a random variable which can assume any value in some interval or intervals of real numbers, and the probability that it assumes any specific value is zero. And proceeding to our next definition, we have the function f of x, which we call here the probability density function for the continuous random variable x, defined over the set of real numbers are if the following three conditions are satisfied: that small f of x is greater than or equal to 0 for all x in R. In other words, all probabilities are non-negative here. Number 2, the integral from negative infinity to positive infinity of f of x dx is equal to 1. Which means that adding all probabilities in the whole of the sample space, the sum is equal to 1. Number 3, that the probability of our random variable in an interval from a to b is equal to the integral of f of x dx from a to b. So here, in the continuous case, we will be using integral calculus, because we cannot add all infinitely many events in the sample space by simple addition. So, adding infinitely many elements is to use the notion of integral calculus here. Now, let's proceed to our first example here. Suppose that the error in the reaction temperature in degrees Celsius for a controlled laboratory experiment is a continuous random variable x having the probability density function of small f of x, which is equal to x squared over 3 when your x is between -1 to 2 and 0 elsewhere. Show that the area under the curve is equal to 1. Letter B, find the probability of your random variable between 0 and 1. Now, solving for our first question, we need to use the second condition of our definition 7 in the previous slide, that the integral of f of x dx from negative infinity to infinity, which is equal to 1. We have the integral of our f of x, which is equal to x squared over 3 dx from negative 1 to 2 is equal to x cubed over 9, because x cubed over 9 is the antiderivative of x squared over 3. And this will be evaluated from negative 1 to 2. So, using the fundamental theorem of calculus, we need to substitute our upper limit of integration, which is 2. So 2 cubed over 9 minus the result when you substitute the lower limit, which is negative 1. So minus the negative 1 cubed over 9. And 2 cubed is 8. So this is 8 over 9 minus negative 1 cubed, which is negative 1. So minus the negative 1 over 9. Minus the negative 1 over 9 is positive 1 over 9. And 8 over 9 plus 1 over 9 is 9 over 9. And obviously this is equal to 1. So this is to show that the sum of all probabilities in the domain of this probability function from negative 1 to 2, the sum is 1. And you can see that 1 using our drawing for this function x squared over 3, because this is just a parabola opening upward, but we have only the domain of our random variable from negative 1 to 2 here. So shading under the curve from negative 1 to 2 using a pink color, we have this area here. And you can check that the sum of all the shaded area here is equal to 1 square unit. So, solving for the second question of the probability of the random variable between 0 and 1, we have the integral of the probability density function of x squared over 3 from 0 to 1, because our random variable is taken between 0 and 1 here. So, solving for the integral of x squared over 3, we have x cubed over 9. Then using the fundamental theorem of calculus, we substitute the upper limit to this integral here. So we have 1 cubed over 9 minus 0 cubed over 9. And 1 cubed is 1, 0 cubed is 0, thus 1 over 9 minus 0. So therefore, the probability is 1 over 9. And this can be illustrated by the green shaded region here, which is the area under the curve from 0 to 1. And you can see that this is just 1 over 9 of this shaded region. Now, let's proceed to our next example here. If the random variable x has the probability density function of f of x, which is equal to kx squared, where your x is between 0 and 3, and then 0 elsewhere, find the following. Letter A, find the value of k in the probability density function. Letter B, find the probability of the random variable x between 1 and 2. So, solving our first question, and in order for the f of x to be a probability density function, we need to use the second condition in our definition 7, that the sum of all probabilities all over the domain is equal to 1. So we have the integral of our PDF of kx squared from 0 to 3, because this is the domain of this PDF, is equal to 1. But we can factor out our constant k outside the integral symbol, so we have k times the integral of x squared dx from 0 to 3, and this is equal to 1. So integrating x squared with respect to x, we have x cubed over 3. And using the fundamental theorem of calculus, we have to substitute our upper limit in the function inside. So we have 3 cubed over 3 minus the function when you substitute the lower limit, which is 0 cubed over 3. So 3 cubed over 3 is 27 over 3 minus 0. And subtracting 0 is just the same number here. So we have 27k over 3, which is equal to 1. And multiplying both sides of the equation by 3, we have 27k, which is equal to 3. And dividing both sides of the equation by 27, we have k, which is equal to 1 over 9. Then therefore, the value of k is 1 over 9 here. And this can be illustrated by the whole total shaded area under the curve from 0 to 3. And we notice that this area is just approximately equal to 1 over 9 of the whole total shaded area. Now, solving for our letter B, which is the probability of the random variable x between 1 and 2, is to use the notion of integral calculus, that this is the integral of our PDF of 1/9 of x squared, since we have already the value of k from the solution in A. So we have the integral of 1/9 x squared dx from 1 to 2. So factoring the constant of 1 over 9 outside the integral symbol, we have 1 over 9 times the integral of x squared dx from 1 to 2. And integrating x squared with respect to x, we have x cubed over 3. And using the fundamental theorem of calculus, we just substitute our limits here. So 2 cubed over 3 minus 1 cubed over 3. And 2 cubed over 3 is 8 over 3 minus 1 cubed over 3, which is 1/3. And 8 over 3 minus 1 over 3, we have 7 over 3. And this will be multiplied to 1 over 9. So multiplying the two fractions, we have 7 over 27, which is the probability value of your random variable x between 1 and 2. So, as in the discrete case, there are many problems in which it is of interest to know the probability that the value of the continuous random variable x is less than or equal to some real number x. Thus, we have a cumulative distribution for a continuous random variable, a parallel notion of the cumulative distribution in the discrete case. Hence, it paves the definition of the cumulative distribution function. If the random variable x is a continuous random variable and the value of its probability function at t is small f of t, then the function given by the big F of x, which is the cumulative distribution function, is equal to the probability of the random variable whose values is less than or equal to the small x. And this can be represented as the probability of your random variable x from negative infinity up to x. So solving this one, this is equal to the integral of our probability density function f of t dt from negative infinity to x, where x is from negative infinity to positive infinity. And this big F of x is called the cumulative distribution function of the random variable x. Now, take note that the properties of the cumulative probability distribution for the discrete random variable also hold for the continuous random variable. That is, the cumulative distribution function value of negative infinity is 0. And also, the cumulative distribution function value of positive infinity is 1. And for any random variable a and b, wherein a is less than b, the cumulative distribution function value of a must not be greater than the cumulative distribution function value of b. In other words, the cumulative distribution function is a monotonic function. As an immediate consequence of the definition above, we have this result here, that the cumulative distribution function is obtained when you add up all your probabilities from negative infinity up to x. And if you get the derivative of your big F of x, this is equal to the derivative also of the right hand side, which is the integral of f of t dt from negative infinity to x. Then, by the fundamental theorem of calculus, the derivative of the integral cancels each other. So this is the small f of x. So you can see that the probability density function is obtained when you take the derivative of the cumulative distribution function, if the derivative exists here. So this result paved the way of this definition 9 here. If the small f of x, which represents the probability density function, and the big F of x, which also represents the cumulative distribution function of x at the small x, then the probability of your random variable from a to b is equal to the integral of small f of x dx from a to b. And this can be obtained by the big F of b minus the big F of a. And this is true using the fundamental theorem of calculus, which we've learned from our calculus subject. So for any real constants a and b with a less than b, and the small f of x is obtained from the derivative of the big F of x. In other words, the probability of a random variable of an interval can be obtained from its cumulative distribution function big F of x. And this can be illustrated in this example here. Suppose that the error in reaction temperature in degrees Celsius for a controlled laboratory experiment is a continuous random variable x having the probability density function of small f of x, which is equal to x squared over 3, where x is from -1 to 2 and 0 elsewhere. Then find the big F of x. Letter B, use the result in A to evaluate the probability of the random variable x from 0 to 1, and then sketch the graph of this big F of x. So solving for the big F of x, we have the integral of the small f of t, our probability density function with respect to t, from -infinity to x. And we know that our probability density function is x squared over 3. So here we will use the dummy variable t here, since x is used as the upper limit. So this is t squared over 3. So integrating this one with respect to t, we have t cubed over 9, evaluated from -1 to x. So using the fundamental theorem of calculus, we need to substitute the limits of integration here. So we have x cubed over 9 minus the -1 cubed over 9. And the cube of -1 is still a -1. So x cubed over 9 minus the -1 over 9 is x cubed over 9 plus 1 over 9. Then therefore, our cumulative distribution function can be written in this way, that when your random variable is to the left of the domain, which is less than -1, the probability is 0 because it's 0 elsewhere in the given here. But when your random variable is from -1 to 2, we have the cumulative distribution function value of x cubed plus 1 over 9, which we solved it here already. And when your random variable is to the right of the domain, the probability is 1 because that is already elsewhere in the domain. And that is how to write the cumulative distribution function given a probability density function. Now letter B, find the probability of your random variable x from 0 to 1. So applying our definition, we have big F of 1 minus big F of 0. And big F of 1, we just substitute that 1 to our cumulative distribution function, which is the big F of x here. So, substituting our random variable 1 to the big F of x, we have 1 cubed plus 1 over 9. And also substituting 0 to our big F of x, we have 0 cubed plus 1 over 9. Now, simplifying 1 cubed plus 1 over 9 here, we have 2 over 9. And 0 cubed plus 1 over 9, we have 1 over 9. So, subtracting these two fractions, we have 1 over 9. And you can check this one from our previous solution when we solve it using the probability density function and not using the cumulative distribution function. Because here, we are using the cumulative distribution function of big F of x in solving for the probability function of your random variable from 0 to 1. Letter C, sketch the graph of the big F of x. And this is the graph of the big F of x, that the probability is 0 to the left of negative 1, meaning there is no probability value. But from negative 1 to 2, the probability is increasing up to 1. And beyond 2, the cumulative distribution function value is 1. Because the domain of the probability density function is only up to 2. Now, let's proceed to our example number 11. If the random variable x has the probability density function of small f of x, which is equal to k times e to the power negative 3x for the random variable x greater than 0 and having probability of 0 elsewhere, then find the value of k here. Letter B, find the probability of your random variable x from 1.5 to 2.5. So, solving for our k, we need to use our second condition from definition number 7, that the integral of our PDF, the probability density function, with respect to x from negative infinity to infinity is 1 here. And because our domain is only greater than 0, so this is having limits from 0 to infinity. So the integral of our PDF, which is k times e to the power negative 3x dx from 0 to infinity, is equal to 1. But factoring our constant k outside the integral symbol, we have k times the integral of e to the power negative 3x dx from 0 to infinity is equal to 1. So, integrating e to the power negative 3x, we use the dummy variable u to represent our negative 3x. So, solving for the differential of u, we have negative 3 dx, because the derivative of negative 3x is negative 3. And dividing both sides of the equation by negative 3 to eliminate negative 3 at the right hand side, we have du over the negative 3, which is equal to dx, because we don't have negative 3 in our integrand there. So, substituting these representations to our integrand, we have k times the integral of e to the power of u. So, instead of writing negative 3x, we will substitute a dummy variable u in behalf of negative 3x. And instead of writing dx here, we will write its value, which is du over the negative 3 here. So, the whole expression is equal to 1. So, factoring again our constant of negative 3 outside the integral symbol, we have k over the negative 3 times the integral of eu du from 0 to infinity, which is the whole thing equal to 1. So, integrating eu du, we have e to the power u. But because our upper limit is infinity, this is an improper integral. So, we will use our technique of limit here. So, k over the negative 3 times the limit of our integral from 0 to t of e to the power u du, where t is approaching to positive infinity. And the whole thing is equal to 1. So, integrating eu du, we have EU evaluated from 0 to t. So going back to the representation of u, which is negative 3x, we have k over the negative 3 times the limit of e to the power negative 3x from 0 to t. And the whole thing is equal to 1. So substituting our limits of integration, we have e to the power negative 3t minus e to the power negative 3 times 0. And because the exponents of e are negative, we need to get the reciprocal of this expression here. So we have k over the negative 3 times the limit of 1 over e to the power 3t minus 1 over e to the power 0. And take note that our exponents of e are positive now because we just apply the law of exponents here. But we know that as t approaches to infinity, the denominator becomes bigger and bigger. So when the denominator becomes bigger and bigger, 1 divided by a bigger number, the result is approaching to 0. So in a limit that is already 0, minus 1 because e to the power 0 is 1. So 1 divided by 1 is still 1. So this is negative k over the negative 3. So multiplying both sides of the equation by positive 3, we have k equals 3. So the value of k in this probability density function is 3. And using this k value to our probability density function, then we can solve our probability of the random variable from 1.5 to 2.5 here. So integrating our PDF, which is 3 times e to the power negative 3x dx from 1.5 to 2.5, we have to factor out 3 here. And then using the same representation of negative 3x, which is u, and dx, which is du over the negative 3 here, we can still factor out negative 3 outside the integral symbol. So we have 3 over the negative 3 times the integral of e to the power u du from u of 1.5 to u of 2.5. Now, integrating eu du, we have eu here. And evaluating this one from u of 1.5 to u of 2.5, we need to go back to the representation of u, which is negative 3x. And then substituting our limits of integration, we have negative of the quantity of e to the power negative 3 times 2.5 minus e to the power negative 3 times 1.5. So multiplying negative 3 to 2.5, we have negative 7.5. And multiplying negative 3 by 1.5, we have negative 4.5. So writing first the positive one, we have e to the power negative 4.5 minus e to the power negative 7.5. So making the exponents positive, we get the reciprocal of these expressions. So 1 over e to the power 4.5 minus 1 over e to the power 7.5, we have approximately equal to 0.0106. So this is the probability value of your random variable x from 1.5 to 2.5. Now proceeding to our next example here, if the random variable x has the probability density function of f of x, which is equal to 3e to the power negative 3x for x greater than 0 and 0 elsewhere, then find our cumulative distribution function big F of x. Letter B, use the result in A to reevaluate the probability value of your random variable x from 1.5 to 2.5, employing definition 9 from our previous slides there. But remember, we have solved this one already in our previous example. But here, we will solve the probability using the cumulative distribution function of big F of x. Letter C, sketch the graph of the big F of x. So, solving our cumulative distribution function, big F of x, we need to use our definition 8 here. So definition 8 states that the cumulative distribution function big F of x is equal to the integral of our PDF of small f of t dt from negative infinity to x. Now take note that we are using here t because x is being used as the upper limit here in the definition. So big F of x, which is equal to the integral of 3 times e to the power negative 3t dt, we can factor out 3 outside the integral symbol. So we have 3 times the integral of e to the power negative 3t dt from 0 to x. And representing this negative 3t as u, we can solve for the differential of u, which is negative 3 dt. But we don't have negative 3 in our integrand. We divide both sides of the equation by negative 3. So this is du over the negative 3. And this is our value of dt. So substituting these representations in our integrand, we have 3 times the integral of e to the power u. So instead of writing negative 3t, we will write its representation, which is u. And instead of writing dt, we will use its representation, which is du over the negative 3. So the big F of x, which is 3 times the integral of eu du over the negative 3 from the u of 0 to u of x, then we can factor out again our constant of negative 3 in the denominator outside the integral symbol. So we have 3 over the negative 3 times the integral of this eu du from the u of 0 to the u of x. So big F of x, which is equal to the integral of eu du, which is e to the power u. So going back to the original representations of u, which is negative 3t, we can use our fundamental theorem of calculus by substituting our limits of integration. So we have the negative of the quantity of e to the power negative 3x minus e to the power negative 3 times 0. And we know that anything multiplied by 0 is 0. So writing first the positive term, we have e to the power 0 minus e to the power negative 3x. And e to the power 0 is 1. So this is 1 minus e to the power negative 3x. And since the big F of x is 0 for all random variables below 0, we can write our big F of x function as 0 probability for any random variable below 0. And it is having a probability of 1 minus e to the power negative 3x for all x greater than 0. And how do I know that? Because I solved already this big F of x here, which is the integral of our PDF from 0 to x. Now, solving our probability of the random variable x from 1.5 to 2.5 using definition 9, we have the big F of 2.5 minus the big F of 1.5. So, applying that definition, we have the big F of the upper limit of 2.5 minus the big F of the lower limit of 1.5. And we know that our big F is 1 minus e to the power negative 3x. And our x is 2.5, so we just substitute it there. Minus 1 minus e to the power negative 3 times our x of 1.5. So multiplying these numbers, we have 1 minus e to the power negative 7.5 minus 1 plus e to the power negative 4.5. And you notice that the signs are reversed because of the negative outside the square bracket here. So writing the first positive term, we have e to the power negative 4.5 minus e to the power negative 7.5, since the 1 here and this negative 1 cancels each other. So we have 1 over e to the power 4.5 minus 1 over e to the power 7.5. By taking the reciprocal of these expressions to make the exponents positive. So, computing this one using your calculator, we have the probability value of 0.0106, where you can check that this is the same answer for the same probability when using the cumulative distribution function. Because in the previous example, we are using not the cumulative distribution function, but the probability density function. So whichever way you will use, you will come up the same answer as long as you just follow the definitions and theorems here. So sketching the graph of our cumulative distribution function, we start the probability value from 0, and then it increases to 1 as x approaches to infinity. So the curve is asymptotic to y equals 1. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.